take a look at number 3. So number 3, what I want you to see from this is that this is actually a pulley. That's all that it is. It's a pulley. But what shape is the pulley? It's a solid cylinder, right? This is a solid cylindrical pulley. So I gave you the inertia for a cylinder there. So what I want you to do, this is kind of like a side view of it, but what I want you to imagine is I want you to imagine rotating it 90 degrees like this. Would you agree with me that if you did that, you would see the picture just like we had yesterday for the disc? And it's exactly the same problem. It's just that all you've done is you've rotated the view 90 degrees so you look like that. Okay, so that basically you just have to remember that this is a cylinder, which by the way, solid cylinder, which happens to have the same equation for inertia that a disc has. So you're going to solve it exactly like we did that problem yesterday, exactly. So look at this. So it says that the cylinder has a mass of 100 kilograms, and it has a diameter of 1 meter, so that means the radius is half of that. So the radius is 0.5 meters. That's the radius. Okay. And it also tells me that there's a 10 kilogram block that hangs from that cylindrical pulley. Okay. So you have a string, lightweight string, that winds around the pulley like this, and then that 10 kilogram mass hangs from it. Now, what I'm going to do is I'm going to go ahead and release this mass, and I know that when I release this mass, it will begin to fall, but it won't be a free fall. Why? Because there are more forces than just the force of gravity acting on an object. There's also this tension. The only way to make it free fall is to cut the string. That's the only way to do it, right? So what I'm going to do, and first of all, let's see what it's asking for. It says, as the cord unwinds and the block accelerates downward, what is the acceleration of the block? Okay. So when you're looking for acceleration, what you want to do in a problem like this, and there's for sure going to be a pulley problem on the test, what you want to do is you want to go ahead and draw a free body diagram for the object that is accelerating in a straight line. Not the one that's spinning, that's the pulley, but you want to draw a free body diagram for the object that is falling, right? Now that object can be modeled as a point, hence why we're calling it a free body diagram. So this is the FBD for the falling mass. Okay, so that's going to be negative mg. That's my force, right? And then I also have a tension, T. Which one should be larger in this case?
mg.
Mg. How come?
It's accelerating down.
We're accelerating down. Okay. So I'm going to go ahead and put an acceleration negative a. Why negative a? Because it's accelerating down, and this is a linear acceleration. This is not a rotational or angular acceleration for something that is spinning. This is literally a tangential acceleration that is due to a change in speed. So we're going to go ahead and sum not torques, but some forces. Because this object is not spinning, it's falling. It's accelerating in a straight line. That's equal to mass times acceleration, not zero this time, because it's not equilibrium anymore. Now I have something that is accelerating, that's speeding up. So I'm going to have tension plus negative mg is equal to negative ma. Why is there a negative sign here?
Because the acceleration is negative.
Acceleration's negative. Acceleration's down. Very good. So now I'm going to have tension minus 10 times 9.8 is equal to negative 10 times a. So I'm going to have tension minus 98 is equal to negative 10a. Okay. How many variables do I have there? 2. The 98 came from 10 times 9.8, right? And then negative 10a. So I have 2 variables. So I need more information. If I'm going to solve for the acceleration, this is what I'm solving for here. I'm going to need to first get another equation. Where is that second equation going to come from?
The torque of the cylinder?
From the pulley, yep, that's right. So I'm going to see how much torque this mass puts on the pulley, on the cylinder. Now, would you agree with me that there's going to be a tension in this cable and it's going to be pulling down on the pulley? Do you agree? Because on the mass, it's pulling up. So would you agree with me that those are action-reaction pairs from Newton's third law? Okay, equal magnitude, opposite direction. So I'm going to go ahead and draw the force diagram on the pulley, right? It's not a free body diagram because I'm not modeling the pulley as a point. I can't, because not all of the points on that pulley are identical, right? For starters, different points are traveling at different speeds. So for sure, it cannot be modeled as a point. So I'm going to draw the force diagram on the pulley itself. Okay, so what I'm going to do is I'm going to go ahead and draw that tension that's pulling down on the pulley, like this. Now, it also has a weight, right? But is the weight of the pulley, which is acting at the center of mass, which is at the geometric center, because the pulley's uniform, okay? Does that weight of the pulley generate a torque?
No.
No, because it's acting at the
Center.
at the center, at the pivot. So that generates no torque. So on the exam, you don't even have to draw it, right? And then also, what it's mounted on, like an axle, that's going to put a supporting force on the wheel, right? Like a normal force. But that also generates no torque because it's at the pivot point, right? So the only force here that's going to put a twist on the pulley that's going to accelerate it in an angular sense, give it angular acceleration, is going to be the tension, which is acting some distance away from the center. So it has leverage. That force has leverage, right? And do I have to break up that tension into components, or is it already perpendicular to the radius?
It's already
perpendicular, right? So what I'll do is I'll first of all tell you that that torque is clockwise. It's going to tend to spin, or accelerate, I should say, the cylinder clockwise from this view. Okay. So the torque will just be F perpendicular, which is T. Remember, don't confuse torque with tension. This capital T is the tension in the cable. This is the twist force that that tension puts on the cylinder, on the wheel. So this is the tension multiplied by the radius. And it's negative because, not because the force is down, but because the torque that that force puts on the cylinder is clockwise. See, if that same tension were on the other side, it would still be a downward force, but the torque would be positive at that point because it would generate a counterclockwise torque on the wheel. So there it is. There's my torque. And that's the only torque acting on the wheel, so that's torque net, actually. It's not just torque, but it's the net torque, because these guys didn't provide any torque, right? Because they were acting at the center. So I remember one of the equations that we had was sum of torques, and it's not equal to 0 in this case because the wheel is actually accelerating, right? It's going to be equal to the inertia of the wheel times the angular acceleration of the wheel. Now, one thing that you have to remember always is that this is just the general equation for that, right?
Just like your text. I don't, but it means you grabbing the pulse and the motion detectors for your
That works, yeah.
You're good with that?
Yeah, because that's a quick setup, so yeah, we're good. Thanks, John. Okay, so then we know that the angular acceleration of the wheel will overall be what? Clockwise or counterclockwise? Clockwise, right? So we're saying that the angular acceleration is going to be negative. So this is just the general equation. So this here is just the net torque. The sum of torques is just the net torque. And we already know what that is. That's going to be negative T times R, right? And then the right side, what would I put in for inertia? Well, this is where you have to worry about what shape is it, right? So what shape is that object?
cylinder.
Cylinder, which has the same inertia as a disc, which I'm going to give you in the problem. Like, I'm going to give you the formula for the inertia in the actual problem, so you'll know what to use for I. Right? So it's going to be 1/2 the mass of the cylinder times the radius of the cylinder squared. That's going to be the inertia. And remember, inertia, or rotational inertia, or moment of inertia, they're synonymous, means resistance to angular acceleration. Okay? How difficult is it to create a twist in this object? And how do you overcome that through a torque? So what we have here is alpha, but technically it's negative alpha in our particular context. Why? Because the wheel will spin clockwise, accelerate clockwise. So look at this. The negative signs cancel. So I'm left with that. Now, would you agree with me that r squared is the same thing as r times r? Would you agree? So I'm going to go ahead and erase r squared, and I'm going to put r times r. Right? So r times r, one of those r's cancels. Right? So we're going to be left with t is equal to 1/2 the mass times the radius Now remember, what did we end up putting in for the angular acceleration in terms of the linear acceleration, as long as the rope wasn't slipping relative to the pulley? What could we put in? Excellent. A over R. We're going to put in A over R. And for our purposes, we're always going to be able to make that substitution, because in this class we'll never consider some rope that's slipping relative to the pulley. In other words, the rope is not going to be falling faster than the pulley is spinning, basically, is what's happening. So that's not going to happen. So basically the rope is falling at the same rate that the pulley at the rim, a point on the rim, is falling at the point that it's there. Okay, so what happens to the radius value? Cancels. So now we're left with t is equal to 1/2 the mass times the acceleration. Yeah, go ahead, Mike.
All right, so why do you have positive?
It used to be negative,
Gotcha,
right?
because both sides have negative.
Both sides had negative, so then these canceled.
Gotcha.
Yeah. Okay, so now I'm going to go ahead and put my numbers in. So I have tension is equal to 1/2. Which mass is this?
Pulley.
That's the mass of the pulley, right? Because that was the inertia for the pulley. That mass came from the inertia of the pulley. So the mass of the pulley was 100, and then times A. So that's going to be T is equal to 50 times A. So that's another equation that relates the tension in the cable to the acceleration, right? So now, what would I do next?
Substitute one of those in.
Substitute one of those into that equation, and then we'll be done. That's it. So we're going to take that T, and we're going to plug it in here, and then we'll be done. So let's do that over here. So the tension is 50A minus 98 is equal to negative 10. So, take a look. I can take the 98 over. I can take the 10A over as well, so that I can isolate all the A terms on one side and all the numbers on the other side. So I have 50A plus 10A is equal to 98. And now, 50A plus 10A gives me 60A, right, is equal to 98. So now I'll be able to calculate the acceleration by dividing, right? So now I'm going to divide by 60. And and remember that you're always really calculating the magnitude of the acceleration. So let's see what that gives us. 9.63? 1.63, okay. And remember that for any of these pulley problems, the acceleration of the falling mass should always be less than the acceleration of gravity. Because remember, it was not free falling unless you cut the string. Remember, there was another force acting on it that was reducing the overall net force on the object. Okay, so that's the acceleration. Now, if I wanted the tension in the pulley, what would I do?
Plug that into.
Plug that back in, yeah. Yes.
So, with the cylinder, when the rope's wrapped around the cylinder like that, it doesn't have any correlation to like how many times it's wrapped or not, right? Like that doesn't
Yeah,
matter.
it doesn't matter.
Right?
Yeah.
Would that only matter if you're considering like slip or not?
Correct. Yeah. Okay, so is everybody comfortable with this one? Is everybody good?